others over break. This is session 2. So in this session, we're going to focus on rules and standards and frameworks that are developed to facilitate the transition towards net zero. So our first speaker is Dr. Dimitrios Rovas. He's an associate professor in smart buildings and digital engineering at UCL IEDE, and he's going to talk about digitalization and digital building twins in the context of this area.
So good afternoon, everyone, and welcome to the second part of today's symposium. So as Anna said, I'm an associate professor in the department, and what I will be talking about today is maybe a very broad introduction in this topic of digitalization and possibly outlining approaches that might have some impact in the future. So what I would like to say is that I tend to be quite broad in today's presentation, but if you like more details, I'm happy to go into more details and drawing upon some of my and my group's work in that space. Now, setting the context, and I know what I'm going to do and present here is an oversimplification of what you saw this morning and more broadly. But when looking and trying to understand how buildings are operating, there's a number of decision points that come into various stages of a building's life cycle. When we're designing, we're running some analysis to understand how the building is going to perform. And if we look at this left-hand side, we can make an estimate about how much energy might be required. And this might be subject to many assumptions. And I think that the discussion this morning highlighted some of the challenges being faced. Now, when going to the actual physical product, not the conceptual simulated product, then we have a number of practical steps that we follow, and then deviations start to appear. So it might be that value engineering happens and our design plans change. It might be that the implementation of the actual practice of construction is not perfect and we introduce deficiencies. It might be that we introduce and use energy management systems, especially for non-residential buildings. And then there's a clear question about how we set this up and how we tune them. And this can lead to good performance, or if, as is very often the case, our commissioning process is not perfect, we can have degradations that might lead to quite big discrepancies. And then once we go into operation, the users come in and they tend to behave not the way we have modeled them. And then as time goes by, degradations happen in systems, the fabric, and everything else. And then the real performance at this very high level is quite different from what we have predicted. And this is very often called the performance gap. And then when we go and realize that our building after a few years is not performing the way intended, we might go back and try to retrofit. And this is very important as the retrofitting and renovation rate is very low, trying to achieve benefits, and these sometimes are not realized in practice. So the question I would like to talk about and maybe present about is how digital technologies might facilitate that process. And in my perception and in my point of view, it is really about the users and how they communicate, how they interact, how they build, how they develop. But possibly technology can provide some valuable insights and tools to facilitate that process. And this is ultimately what can support delivery and delivery optimization. So what I would like to highlight is look at different phases of this life cycle that is quite common and quite well known to all of you here, I assume. And then look at how some of these digital tools can facilitate, and then highlight this concept of digital twins, which I feel is one term which is used and abused quite often, but highlight that there is maybe some interesting ideas there that can potentially lead to some interesting insights. Now, before I start and go into these details, what I would like to do is I would like to introduce some definition. And when talking about digital twins, one thing that can come across is that everyone pretty much understands something similar. And the reason why this term is very attractive because it relates and resonates with a lot of people. But basically, the definition that we're giving might sometimes be off compared to what we understand. So what I adopt in my presentation, because it gives some sort of context, is one of these definitions, Some definitions tend to be quite broad and focusing kind of that digital virtual counterpart with the physical. Others are quite application specific and therefore imply and assume a lot of context. And this one by the Institute of Engineering Technology kind of highlights is somewhere in between and kind of highlights something that I think is quite important in terms of understanding what are the ingredients. The part about the definition that I got from this report focuses very much on that digital representation. But then if we drill down to the details, it suggests a process rather than a very specific definition. We can have different digital twins, virtual representations. And then these virtual representations can be of varying complexity. And I think that is very important, as in every modeling exercise, that varying complexity needs to be, we need to have a model that is complex enough to be able to serve that specific purpose, but not too complex because otherwise it becomes less useful or not useful at all. And then it introduces also that notion of connectedness between the virtual and the physical. And I think that is quite important because this is where things are starting to become interesting. And then the concept of maturity, which is this table, and it says that we might have digital twins that are very simplistic, and probably we would not call them as such, like capturing the reality and digitization in the most classical sense. And then it kind of shows a pathway kind of going from low complexity to high complexity. And the pathway involves having some sort of information context to represent aspects which are important, and then possibly linking that with actual real data. And that two-way data interaction between the physical and the virtual is where the true value comes in and where the opportunity lies. And basically that pathway is a pathway for delivery of digital twins, and possibly, if we think there is a value there, exploring and exploiting that value. Okay. So I would like to kind of highlight before I go to that one aspect, which is the aspect that what comes here or becomes clear from this is that we need some sort of information. And that is very often an information model. So there is an information modeling exercise. And then we need to connect with the physical side and get the data and then couple those two. So BIM or information models and so on. So I'm going to highlight some results from some research projects and some work I have been doing. The first part is an example of renovation, kind of going at this end of the time. And I think that problem of retrofitting and renovation is a very important one, as has been discussed this morning. The problem is that buildings like this, so this is an example of a building in Spain, are very information poor because they have been built 20 or 30 years ago. And all the data that we have, if we have any data, are not very good quality at all. So what we can do is we can try to digitize and create digital versions. And this can be captured in the form of building information models, which, like energy or simulation models that we're more comfortable or confident with, have various representations and various levels of details. And what I have highlighted here is kind of two such pathways that we've explored in the project. One is to do a scanning and create point cloud data, process this using some machine learning approaches, import this to model editing tools, into building information modeling tools like Revit, and then export that. Or the other pathway is to take whatever information we have, like 2D plans from the previous era, and then digitize this and create the 3D model and pass this. Now, the problem, and maybe the lesson learned, is that when we think about a BIM model or any information model, we need to articulate what is included in that model. And so it is geometry, which is very obvious and very evident, but it might be other information like process-related information, thermal properties, and other such aspects. So we have to be very clear about what the information requirements are and how the modeling process has to happen if that information is to be useful. And what you will find, as we found in this practical case, is that data quality is very important. And so the world is not perfect. So if we take Revit, for example, and this is a very simple case study that we did, so it's a national building, and we use the default Revit exporter, what we find is that the exportation is not perfect. So the information that we're writing out of that modeling process sometimes is problematic. And not only that, it might be that the model that we're creating might have issues. For example, what you're seeing here is walls going to each other, so classes, spaces intersecting with spaces, things that are not so visible, but are important when we're trying to consume that information to provide anything useful. So, and also what we're missing is we might be missing certain information. For example, if we want to create an energy model, which is very important in the relevant context of retrofitting, because we would like to understand and evaluate different design alternatives, then that information might not be there, and we might have to post-process it. So we might increase or add additional information, which can be used to map or to create that mapping. So what we have been looking is how to facilitate those tools. And so each one of them can be a separate paper or a separate presentation. But what I would like to highlight is some of the headline lessons learned. And these are that we can create some digital representations. And the important part about why it is important today is that this can happen at an increasingly lower cost. And I think that is what is important, is that the value of data or the cost per data point or the cost per model has come quite low, to the point where this can be more ubiquitous and more useful or can be more easily used in practice. And then we could, for example, use these mapping approaches that I have been hinting about to generate this digital counterpart, which is an energy model. In this particular case, it's just a visualization of an energy plus model, but do so automatically. So we have been working into kind of taking that information model, generating the corresponding energy model, and then set up an optimization context by which we can say, let's try different design alternatives or different retrofitting alternatives. And then we can explore that space of possible configurations and find ones that seem to be more appealing in the multi-criteria optimization context. So what I spoke so far has been, and very quickly, has been that point of going from and collecting static information about a building. And then what I can talk about, or what I would like to go, is kind of start pushing the boundary down, kind of going how we get and collect actual information data, actual data from sites. And maybe this is also an interesting point to raise. So what you're looking here is a setup and some hardware that has been developed within the group. And this is a very low cost, so something like £100, hardware and sensors, that basically allow to monitor a student room and capture the relevant environmental parameters. And the important part is we can do it in real time and then compute, store the data and analyze them to answer questions that might be relevant. And so I think this idea of having low cost data, real-time data, is an interesting one, because combined with that context that is captured by the information models, forms the basis for a number of interesting opportunities related to how we extract information out of data. Now, if I have to go into the details, and I'm not going to do that, but I would like to highlight, is that there are complex ways of getting the data and facilitating that data extraction. And this in the ICT world is called middleware platforms. We were working on one which we have developed in the project. And this is a commercial one called Tridium, which is marketed and sold by Honeywell. And it's quite often used in big commercial installations. And both of them have similar characteristics, and it's an information technology problem, but a very important one if we want to access data in a unified approach. Now, once we do that, we can start thinking about how we can exploit the data. And so what I'm going to present here is some sort of idea. So we have the building or a group of buildings, and we understand the building not as a system or a component in isolation, but rather as a system that is comprising of a number of individual components, all of them interacting together. This is the passive elements of the building, like the construction, facade, glazing, and so on. Aspects like active elements, heating, cooling, renewable sources installed, photovoltaics, and so on. And I think the more important part is the end users that are interacting with this, and the external disturbances, which is the weather. So the approach, or the way we're viewing the building from the mathematical perspective, is as a complex system of systems. And therefore there is an emergence, and that emergence can be that once you have a complex system of systems with many actors and factors which are uncertain, it might be that you have emergent properties that you might not artificially and a priori design for. And so it is important to understand how to influence those factors or control some of these factors, but acknowledge at the same time that that process is not going to be perfect, and therefore what we need possibly a way to account for these emergent properties or emergence in general. Now, what we did here in this particular project is the following. We captured a couple of buildings. We have this middleware to facilitate that two-way process, what I showed in the previous slide. And then on the other side, we have the virtual counterpart, which was a thermal model. It can be a black box, a white box, a gray box model. There's a lot of research happening about what is the structure that is the most appropriate one. And then on top of this, we can have some sort of optimization context. And then what we can do, if we go here on the right-hand side, we can query the optimization for different operational parameters, how we set the set point given certain aspects. And then once we've done virtually that evaluation, send back that command to the building and interface with the real world. And that is really becoming something that looks like a real digital twin, where we have information coming out of the building, we calibrate or we design the model, we make a decision, we communicate that back to the building. And what did we learn by that? So we did a number of experiments. And as I said, there's quite a lot of approaches. There's a lot of details. It's a whole field in our domain. But what we find is that building characteristics can influence very much the operational performance that we're achieving. And so we've done experiments in this building, which is south-facing, thick walls, high thermal mass, a lot of glazing, a lot of energy systems. So this is again in Germany, a lightweight building in Southern Europe, and the characteristics are very different. But the problem was, or the issue or the findings was that while we can do all those fancy ideas and approaches where we use the building, in reality, what is the best performance can be very usually captured with very simple or relatively simple control sequences that are tied and linked to that specific building. And ASRA is in fact working on that, and they're developing something called Guideline 36, which is a set of sequences that capture this, which they call advanced control sequences, but they're quite easy to implement in a context on an energy management system, and they cost much lower than the cost of developing these models and facilitating that two-way process. The other part, which is quite interesting, and I'm not going to be quantitative here, but I can give more evidence if you like. But the other thing which is quite interesting is that emergence that I talked about. And this is one example. That is an example from the building in Aachen. And what we found there was that the base heating was supplied by a slow thermally activated building slab in the ceiling. But then we had facade ventilation units here on the two sides. So this was one office in that building in Aachen. And while the building was meant to be providing or supplementing heating to the end user, or to supplement the main heating source, which was this one, many times the system was not interlocked, and that happens with many buildings. And what we got simultaneous heating and cooling. So basically burning energy without doing anything. So while operational optimization in the context of control is very important in the context of commissioning, understanding and identifying faults like this one, which happens in many buildings, potentially gives a lot more opportunities in terms of energy saving. And so data and processing the data can help identify those emergent properties that might not be visible to the real eye, but can provide an opportunity for tuning performance and reducing that performance gap. Okay, so what we've then done is ask that question of how can we deliver this at scale. And so again, here is the building. It doesn't look like a building. It looks like a collection of assets. And then the idea was that we could embed and deploy analytics at different scales, from embedded hardware, which was very close to the building, to local servers, to the cloud, and then asked what is the structure or infrastructure by which we can do that. And started developing the technology stack, but also kind of demonstrating how that would work in practice. And so the idea, and this kind of shows the concept, is that we can generate some information from BIM models. We can ask aspects related to the topology, connectivity of spaces, placement of sensors, that information. Overlay, for example, other aspects related to thermal properties or heating and cooling systems, and create a representation which looks like the one on the left. So this is a knowledge graph And kind of that represents a thermostat, which is connected to another system, which is connected to data, and create that representation in terms of knowledge graphs that represent the asset. So it doesn't look anything like the asset on the right-hand side, which is a building in Greece in that particular case. But rather, it allows us to capture that complexity and that informational context, which is very important in deploying and developing those analytics, or as in this case, dashboards. And it allows us to ask and answer questions related to overheating, related to energy use, related to comfort, or whatever context we want to look at, like health and well-being, energy sustainability, operational performance, and costs. So with that, I had a few more slides, but I think I'm going to skip through that. But I would just like to point out that we're investigating this in the context of an international collaboration, which is called IEDE Annex 81 on data-driven smart buildings. And we're collecting case studies and trying to understand how some of those components that I briefly touched upon, representation of information, delivery of information, data collection, data integration, and data analytics can come together. And we have a number of reports that I can point you to, kind of trying to synthesize what is our understanding and maybe what are the opportunities for further development. And I'm working and kind of co-leading one of these subtasks. And with that, I'm going to very quickly go to the end and then conclude with maybe a very brief summary, and then happy to talk about that later. The conclusion is that maybe some of these ideas of data-driven ideas, whether you want to call them digital building twins or whatever you want to call them, are quite important and quite relevant. And they're quite relevant in the context of facilitating user interaction, user interfacing, and end user requirements. We can deliver and are developing the software stack and knowledge to deliver this at scale. And I think this is what is quite important. And there's a very clear value proposition that is demonstrated, but still evidence in broad scale is limited. So I think there is a point of research there in collecting evidence and highlighting what the value proposition is to different stakeholders. And technology is supporting of that process. It's not the main player, it's not the main actor, but rather enabling us to ask questions and to explore aspects with a level of detail that has been not possible in the past. And I think that is where the true value lies. And with that, I would like to finish and thank you all and happy to take questions.
Thank you so much. So I think we have time for one question. Yes, please. Can you also please introduce yourself?
My name is Gaurav and I thought it would be similar to my question is just like simple one. When you are making a decision for all together, how do you ascertain the thermal properties of the fabric? Because you were touching upon the measurements that you're taking out from the actual to the model. But there was also mention about the fabric parameters. Do you assume generic values from data from the NCM, or do you actually do a physical test for the fabric?
Okay, so I think that's a very good and valid question. So the answer to that is the following: we use whatever information is there. So in some of these models that I was talking about control, and I haven't talked about the results, we went and did actual physical measurements to get U values and to get them as close as possible. But when we don't have that information, we can use aspects related to that comes from standards or NCM or what have you, depending on the year and so on, with the understanding that there is an implicit uncertainty. And I think the important point, and I think it's a whole branch, is that we need to understand that our models are inherently uncertain in one way or another. Even when we do a measurement, it's just that the uncertainty is lower. And then a part of this discussion is understanding how that uncertainty propagates when we're talking about digital twins. And the biggest uncertainty in that particular case, it's not the physical parameters, but it's the actual users. So I think we've experienced that discrepancy. And in fact, I think there's a very active line of research. For example, Farhan is working on this, on how to understand the role of the users, how to model, how to understand the uncertainties, and then how to propagate these uncertainties from inputs to outputs and understand the input. And I think in developing useful digital twins, we have this balancing between accuracy and level of detail, and less level of detail, but also we have to incorporate this uncertainty quantification. And in fact, there's a field within statistical science that is focusing very much on this in that context. Yeah, I think that's a very good question.
Great, thank you. And there will be more opportunities